Time, we live by it, plan our days around it, and yet, its true nature remains surprisingly elusive. You're tuning in because you're keen to understand the deeper workings of our universe, maybe without getting bogged down in all the jargon, and, well, that's exactly what we're about here.
Exactly. Today we're plunging into a concept that honestly sounds like science fiction, but is actually a fundamental aspect of reality. Time dilation. Our aim is to not just define it, but explore its real-world consequences and how it utterly transforms our sort of intuitive understanding of time.
Right. And just to set the stage a bit, we're talking about two main ways time behaves differently than we might expect, both thanks to Einstein, really. First, there's the time dilation caused by motion that comes from his special theory of relativity. And then there's time dilation due to gravity, which is a key part of his general theory.
Yeah.
Okay, so where should we begin to unpack this mind-bending stuff?
Well, let's start at the beginning with Einstein's special relativity. That was a groundbreaking piece of work from 1905. It's basically built on two ideas that might seem simple, but wow, they have incredibly profound implications.
Okay.
The first is that the laws of physics are the same for everyone, no matter if they're standing still or moving at constant speed. Inertial observers, we call them.
Right. That one feels kind of logical, I guess.
Yeah. But the second one, and this is where things really get interesting, is that the speed of light in a vacuum is constant for all observers, regardless of their own motion or the motion of the light source.
Okay, hold on. That second one, that's a real head-scratcher. If the speed of light is always the same no matter what, then what else has to give? Something's got to change.
Exactly. That's the crucial question. Imagine you're on a train, you throw a ball forward. To you, it's moving at one speed.
Yeah.
But to someone standing still outside, watching the train go by, it's moving faster, right? Because your speed adds to the ball's speed.
Sure, makes sense.
Now, imagine the ball is a beam of light. This principle says, no matter how fast your train, say, your spaceship is moving, that light beam will always appear to move at the same speed, speed c, to both you and the person standing still outside.
Huh. So it doesn't add up like the ball.
It doesn't. And to make that work, to keep the speed of light constant for everyone, something else has to adjust. And that's something else. It's time.
Time itself.
Time itself. According to special relativity, if you're moving really, really fast, like a significant fraction of the speed of light, time will actually pass slower for you compared to someone who is standing still.
Slower. Not just feel slower, but actually tick slower.
Genuinely tick slower. It's not a matter of perception. It's a real physical difference in how time unfolds in those different situations, those different frames of reference.
Wow. Okay. And there's a formula that explains exactly how much slower, isn't there? The Lorentz factor. Can you give us the lowdown on that without making my brain melt?
I'll try. Absolutely. Essentially, this formula tells us by how much time will slow down for a moving object compared to a stationary one.
It looks like this.
Simple syllables. Let's break it down.
Right. So, a delta t prime is the time interval measured by a stationary observer, like someone on Earth.
Okay.
8 delta t prime is the time interval measured by the moving observer, say, someone on that fast spaceship.
Got it.
8 iter is the speed of the moving observer, the spaceship speed, and c is the speed of light, that universal constant.
Okay, let's try to visualize this. That v squared over c squared part. If your speed v is a really big chunk of the speed of light c, then that fraction, v squared over c squared, gets close to 1.
You've got it, exactly.
So you're subtracting a number close to 1 from 1 inside that square root.
Which makes the number under the square root really, really small, close to 0.
Okay.
And the square root of a tiny number is still a tiny number. So the whole bottom part of the fraction, the denominator, becomes very small. Right. And when you divide the original time flight, a tiny number,
the result becomes a much larger number.
So 8. The time measured by the moving person is less time passing for them, while 8, the time for the stationary person watching them, is more time passing. Did I get that backwards? I'm your phrase.
Almost. Let's certify. 8 is the time measured by the stationary observer. Let's call it Earth time. It's the time measured on the moving clock, the spaceship time. The formula actually shows 1 VCC. So since the square root part is less than 1, spaceship time is less than 8, Earth time. Less time passes for the moving person.
Okay, got it now. Less time passes for the speedy traveler. The moving clock ticks slower from the stationary person's perspective.
Precisely. It's as if the fast-moving clock is ticking in slow motion relative to the stationary one.
That's truly bizarre to think about. But is there actual, real-world proof that this happens? It's not just some theoretical curiosity.
Oh, absolutely, there is indeed. One really compelling piece of evidence comes from these tiny particles called muons.
Muons.
Yeah, they're subatomic particles, kind of like heavy electrons. They're created way up high in our atmosphere when cosmic rays particles from space smash into air molecules. Now, the thing about muons is they're unstable. They decay incredibly quickly, in just a couple of millionths of a second on average. Their half-life is very short.
Right. So based on how fast they move, even if it's really fast and how short their lifespan is, they shouldn't really be able to travel very far before they just poof, vanish.
Precisely.
Yeah.
If you just use classical physics, their short lifespan means very few should actually make it all the way down from the upper atmosphere to the Earth's surface before decaying.
Oh.
But scientists detect a significantly larger number of them reaching detectors at ground level than those classical calculations would predict. Way more.
So how does time dilation explain that?
Well, what's fascinating here is that these muons are traveling incredibly fast, like 99-point-something% of the speed of light.
Well,
So because of their high velocity, special relativity kicks in. Time dilation means their internal clocks, from our perspective standing here on the ground, are running much, much slower.
So their couple of millionths of a second lifespan gets stretched out.
Exactly. It effectively stretches out their lifespan, from our point of view, just enough for a significant number of them to survive the journey down to the surface. It's like their internal reality is playing out in slow motion relative to us, giving them more Earth time to travel the distance.
Wow. So these fleeting little particles are actually living proof that time isn't this rigid universal metronome we always assumed. That's amazing. Okay, so that's the time dilation we get from speed, velocity. Now, what about the other kind? The time-bending effects of gravity.
Right. That takes us to Einstein's next big theory, his theory of general relativity, which he published about a decade later in 1915. And here, he gave us a completely new way to think about gravity. Instead of seeing it as just a force pulling objects together like Newton did, Einstein described gravity as the curvature or warping of space-time itself. Space-time being this four-dimensional fabric combining space and time.
Okay, the classic analogy is the bowling ball on the rubber sheet.
Right,
Yeah.
that's the one. Imagine placing a heavy bowling ball on a stretched rubber sheet. It creates a dip, a curve, and that curvature influences how other objects, like marbles rolled nearby, will move. They follow the curve.
Right, they curve towards the bowling ball. So the more massive the object, the bigger the dent it makes in space-time.
Exactly. More mass or more energy means more warping of space-time.
And how does this warping of space-time affect time specifically?
Well, according to general relativity, the stronger the gravitational field, which corresponds to a deeper curve or warp in spacetime, the slower time passes.
Slower, again.
Again, but this time because of gravity, not speed. Conversely, in weaker gravitational fields, further away from the mass, time passes more quickly.
So wait, if I'm standing on Earth, time ticks slower for me than for someone floating way out in space, far from any planets or stars.
That's precisely it. The closer you are to a massive object, the slower time will tick for you relative to someone further away in a weaker gravitational field.
So time isn't just relative to how fast you're moving, but also to how strong the gravity is where you are. That's wild. Doubly relative.
Exactly. Wild is a good word for it. And again, like with special relativity, there's a mathematical description for this. For a simple case, like a non-rotating spherical mass, it's related to something called the Schwarzschild metric. A simplified version of the time dilation part looks like this. G2EMRC.
Okay, more symbols. Let's see. GRC are the time intervals again, right? Time far away versus time close to the mass.
Correct. G is a time measured by an observer far away from the mass, where gravity is negligible. GO is the time measured by an observer within the gravitational field at a distance r from the center of the mass m.
Okay. And G is gravity constant.
Yep, Newton's universal gravitational constant. M is the mass of the object creating the gravity, like a planet or a star. R is the distance from the center of that mass. And C, as always, is the speed of light.
So the important part seems to be that 2gm over rc squared bit.
Exactly. Focus on that term. If you have a larger mass, m, or if you get closer to the center, a smaller r.
Which means stronger gravity.
Right. Stronger gravity makes that whole fraction 2gmrc larger.
Okay. So inside the square root, you're subtracting a larger number from 1.
Which gives you a smaller result under the square root, a number less than 1.
And multiplying time far away by this number smaller than 1 means that time close to the mass is smaller. Less time passes.
You got it. Time passes more slowly in the stronger gravitational field. Gravity literally puts the brakes on time, you could say.
Is there any real-world evidence for this gravitational time dilation too? Like the muons for the speed effect?
Absolutely. A very direct and famous piece of evidence came from the Hafeel-Keating experiment back in 1971.
Hafeel-Keating, what did they do?
Well, Joseph Hafeel and Richard Keating took these incredibly precise atomic clocks, like super accurate clocks. They synchronized them. Then they flew some of them around the world on commercial airplanes, once eastward and once westward.
Flying clocks. Okay.
And they compared the time recorded on these traveling clocks to identical atomic clocks that stayed put on the ground at the U.S. Naval Observatory.
Did they see a difference?
They did. Tiny differences, nanoseconds, but definitely measurable. And crucially, the differences perfectly matched the predictions made by combining both special and general relativity.
Both. How so?
Well, the planes were moving fast, so special relativity predicted their clocks should slow down relative to the ground clocks. That's the velocity effect.
Okay.
But the planes were also flying at high altitude, further from the Earth's center than the ground clocks, so gravity was slightly weaker up there. General relativity predicted their clocks should speed up slightly due to the weaker gravity.
Ah, so two competing effects again.
Exactly. And the net difference they measured depended on whether the plane flew eastward with Earth's rotation or westward against it, which affected their speed relative to a non-rotating frame. The results confirmed the combined predictions beautifully.
That's pretty mind-blowing, actually flying clocks around the world and seeing them tick at different rates because of speed and gravity. It makes this abstract physics feel incredibly real. So these aren't just quirky effects that only matter in labs or for physicists arguing about muons. Do they actually have any impact on our everyday technology or how we live?
They have a surprisingly significant impact, actually, especially on technologies we rely on constantly, maybe without even realizing it, like the Global Positioning System, GPS.
GPS. How does time dilation affect my phone finding my location?
Think about it. GPS relies on a network of satellites orbiting the Earth. These satellites are moving very fast, maybe 14,000 kilometers per hour.
Right.
And they're also orbiting quite high up, about 20,000 kilometers above the surface, where Earth's gravity is significantly weaker than it is down here.
Okay, so they've got both effects going on again, moving fast.
Means their clocks should run slower, according to special relativity. About 7 microseconds per day slower than ground clocks.
And being in weaker gravity.
Means their clocks should run faster, according to general relativity. About 45 microseconds per day faster.
Ah, so the gravity effect is actually bigger in this case.
That's right. In the case of GPS satellites, the general relativistic effect, faster time due to weaker gravity, outweighs the special relativistic effect, slower time due to velocity.
So overall, time actually runs a little bit faster on the GPS satellites compared to down here on Earth. By how much?
Correct. The net effect is that the clocks on the GPS satellites tick faster than identical clocks on the ground by about 38 microseconds, or 38 millionths of a second, every single day.
38 microseconds? That
Right there.
doesn't sound like much. Does it really matter?
It sounds tiny, but GPS relies on timing signals with nanosecond precision. If these relativistic effects, this net 38 microsecond per day difference, weren't meticulously accounted for in the GPS system's calculations,
Yeah. What would happen?
the positional errors would accumulate incredibly rapidly. We're talking errors building up at a rate of about 10 kilometers per day. Your GPS would be useless within minutes.
Wow. Kilometers per day. So the fact that my phone can pinpoint my location with, pretty decent accuracy is direct proof that these corrections are being made.
Absolutely. It's a fundamental validation of Einstein's theories playing out in your pocket or your car's navigation system every single day. It's essential technology.
That really puts it into perspective. It's not just some obscure physics concept. It's essential for something as commonplace as finding directions to a new restaurant. What about in other areas of science? Does time dilation play a role there?
Oh, definitely. In high-energy physics, for instance, particle accelerators like the Large Hadron Collider at CERN.
Yeah.
They smash particles together at speeds incredibly close to the speed of light. These particles experience enormous time dilation.
Like the muons, but even more extreme.
Much more extreme. This effectively extends their very, very short natural lifespans from our laboratory perspective. This extra time allows researchers to actually study their properties and how they interact in much greater detail than would otherwise be possible. It's crucial for understanding the fundamental building blocks of matter.
Okay. And I can't help but think about the implications for space travel, especially, the science fiction dream of going to other stars. I remember hearing about the famous twin paradox.
Ah, yes, the twin paradox. It's a truly classic thought experiment that really highlights just how counterintuitive time dilation can be.
How does it go again?
Well, imagine you have two identical twins. One, let's say, stays here on Earth. The other twin hops on a super advanced spaceship and takes off on a long journey through space, traveling at a significant fraction of the speed of light, say 90% the speed of light, out to a distant star and back.
Okay. High-speed journey.
According to special relativity, because the traveling twin is moving so fast for a prolonged period, time passes much slower for them compared to the twin who remained on Earth.
So, when the spacefaring twin returns,
They would actually be biologically younger than their sibling who stayed behind on Earth. Years younger, potentially, depending on the speed and duration of the trip.
younger, that sounds like something straight out of a movie. But based on everything we've discussed, the physics actually backs this up, at least in principle.
It does. While we haven't yet sent humans on interstellar voyages at near-light speeds, the engineering challenges are immense. The principles of time dilation are very well established. They've been repeatedly verified through experiments with particles and clocks, like we discussed.
So the paradox isn't really a paradox in the physics sense. It just feels paradoxical to us.
Exactly. The paradox arises mostly from applying intuition incorrectly, or forgetting that acceleration is involved for the traveling twin to turn around, which breaks the symmetry. But the core effect, the differential aging, is a real prediction of relativity. It underscores the fundamental reality that time is not universal. It doesn't tick at the same rate for everyone, everywhere.
This really forces you to step back and reconsider some of the most basic assumptions we have about the world. For centuries, we've thought of time as this steady, reliable march forward, the same for all of us, like a universal clock ticking away.
The Newtonian view.
Yeah. But relativity just paints a profoundly different picture, doesn't it?
It absolutely does. Time dilation fundamentally challenges that Newtonian idea of absolute universal time, the notion that there's a single cosmic clock dictating the pace for the entire universe. Relativity reveals that time is, well, relative. It depends on the observer's motion and their location within a gravitational field. It's a much more flexible and frankly stranger reality than we thought.
And this leads to some pretty deep philosophical questions too, doesn't it? I've come across this idea of the block universe. How does time dilation fit into that kind of thinking?
Yes, the concept of a block universe is one really intriguing, though not universally accepted, interpretation that stems from relativity. If time isn't absolute, and if space and time are interwoven into this single entity, space-time, then some interpretations suggest that all moments in time, past, present, and future, might, in a sense, coexist within this four-dimensional block.
Coexist, like the dinosaurs and my breakfast this morning and whatever happens next Tuesday are all equally real somewhere in this block.
That's the gist of the idea, yes. In this view, the flow of time that we subjectively experience might be more like an illusion, perhaps a result of our consciousness moving through this static, pre-existing space-time structure. It's a perspective where all of history, from the Big Bang to the heat death of the universe, exists simultaneously, laid out like scenes on a film reel.
So in this view, the future isn't something that's going to happen. It kind of already exists, in a way, just like the past and the present. That's a seriously mind-bending concept to wrap your head around.
It really is.
Yeah.
And it's definitely a topic of ongoing discussion and vigorous debate among both philosophers and physicists. Is space-time truly a static block we just perceive sequentially? Or is there a more fundamental, perhaps emergent nature to time and its apparent flow that we haven't yet fully grasped?
It seems like time dilation doesn't necessarily prove the block universe, but it points towards time being much weirder than we think.
Exactly. Time dilation provides compelling empirical evidence that our everyday perception of time as this simple, uniformly progressing phenomenon is, at best, incomplete and possibly fundamentally misleading about the underlying structure of reality.
It's incredible how delving into something as seemingly straightforward as, how time passes can lead us to such profound and perplexing questions about the very nature of reality itself.
Absolutely. Time dilation is far more than just a theoretical oddity or quirky prediction. It's a well-supported pillar of modern physics, deeply rooted in Einstein's revolutionary theories. It's backed by a wealth of experimental evidence, from muons to atomic clocks, and as we saw, it's absolutely crucial for technologies that underpin our modern world, like GPS.
Yeah. So we've kind of journeyed from this old view of time as a constant universal heartbeat to understanding it as something much more malleable, something that can stretch and compress depending on how fast you're moving or how strong the gravity is around you. It's a total transformation in how we perceive reality.
Precisely. Time isn't just the fixed stage upon which the universe plays out its drama. It's an active participant, intimately intertwined with space, with motion, and with the very fabric of gravity itself.
Well, this has been a truly deep dive into a truly fascinating and fundamental topic. So, to leave you, our listener, with something to really chew on, if our experience of time, the very flow of moments, is indeed relative, if it depends on our circumstances, how does that fundamental truth reshape how we see our own lives, our own fleeting moments, and maybe even our place within the vastness of the cosmos? Is time a river flowing around us, or are we perhaps the ones moving through a still and boundless ocean of space-time? Just something to really let sink in.